Welcome to Breadboarding. In the previous video we managed to get our modern surface mount serial controller UART chip working on a 48-pin DIP connector here that we made. We managed to download programs into the computer memory using the S-record format. Now this is video 8 in the Breadboard 8088 PC version 2, and in this video we're going to be looking at adding the power on self-test and timer, and we'll be looking a bit about what makes a computer IBM PC compatible. So here's our plan. We've completed the basic nanocomp. So this is a simple computer based on the 8088 processor with an LED display, keypad and a serial port to allow us to upload and download program files to the system. And in order to make a basic floppy disk PC, we need to carry out these steps. So we're going to start with the power on self-test port and port B as it's known, which I'll explain about in a minute. The timer and the speaker, so we can get beep codes and we can get feedback actually from sound. And then as we go through the next couple of videos, we'll be adding the interrupt controllers, real-time clock, PS2 keyboard controller. We'll then actually try and get Sergey Kiselev's XI8088 BIOS up and running and see what sort of messages we can get from that. We're then going to spend quite a bit of time looking at them building a CGA compatible video controller. We're going to start initially with the text mode, then we're going to add the floppy disk controller and see if we can boot MS-DOS from floppy disk. So in the first video I covered in summary what we were building. This is really a PCXT hybrid, and this uses, where possible, fairly modern components rather than using legacy 40-year-old components. So we're going to be trying to use MS-DOS 3.3.0 and early versions of Windows. As I said, we'll be building out the CGA graphics controller in later in the series. What we've done already is in green here, so we've got our clock CPU bus controller and some of our bus signals, and we also got the serial port running. This was the 16550 compatible serial port, and we're also going to be adding the power on self-test port as well. Now, power on self-test I'll talk about for a few minutes. Now, the original PC and PCXT didn't actually have a power on self-test port, but the PC-AT did actually introduce a basic level of this, and it included a couple of outputs from the BIOS as the system was booting up. But over time, the BIOSes would actually output quite a few diagnostic codes. They weren't really error codes, they were really sort of a status code to see how far in the boot up process that the BIOS has got. -0degrees.net has a section on ISA postcards, and you can see that the original PC didn't support power on self-test codes. Later PCs did, and a sort of a power on self-test card. This is an example of a more modern one that you can still buy today, and it has not only the original ISA bus but also PCI bus here as well. It will generally show the last power on self-test code before the computer halted. And this is a vintage card as well, and again, not really error codes, it's just really a status of how far things have got. And one of the things you'll notice is that the port number used for power on self-test does vary by different PCs. So generally port 80 is what's used by standard, and certainly Sergey Kiselev's design used port 80. You can see that the PS2 used port 90, and a micro-channel bus PC such as the later models of PS2 used the higher ports. But we'll be using port 80, and all that happens is in the BIOS, there will be a code written to port 80, and if we have the appropriate device attached to that, so I'll be using a logic analyzer, we should be able to actually see the code, and it's quite useful for producing diagnostic information. Certainly with a floppy disk controller, I was outputting all sorts of information to the power on self-test port to be able to provide diagnostic information. So let's have a look at the block diagram and just work our way through the bits that we've already done. So we've got our 80C8088 processor. This is a modern processor which can still be purchased today. I think it's about £40 from Mauser. We're running this both with the original default clock on the PCXT but also a faster turbo clock, and we will need that when we want to use the floppy disk controller, particularly if we're not using direct memory access. We've added our buffers, latches and bus controller, address decoding. We've got our read-only memory, which is currently running the nanocomp monitor that runs the display and keypad. We've got actually 640K of RAM. We've also added something which wasn't in the original PC. This is the keypad and 7-segment port, which we then used for driving a 7-segment display and the keypad. And then we added the serial port. Now, only really the 7-segment display port and the keypad here is not PC compatible. So these weren't really on the original PC platform. We've just added these, give us some sort of debug support as we're developing the computer. The rest of all these things, though, are actually IBM PC compatible. So what actually makes a computer IBM PC compatible? So we obviously need to be using an Intel 8086 or 8088 compatible instruction set. So we're using the 8088. We need to have a BIOS which is compatible with the IBM PC software interrupts. So this is the way how DOS interacts with the BIOS, generally through software interrupts. There are certain devices that the PC expects to have, so things like the timer, the parallel peripheral interface, port B, and speakers, particularly for the power on self-test beep code. So if there's a fault with the memory, for example, then you might get some beep codes. We need to make sure that the I/O ports and interrupts are similar to the PC, or at least the BIOS is configured if there are any differences. We're likely to want to have some PC ISA type expansion bus, or at least make sure the signals that we've got on our bus are PC compatible. We need to add interrupt controllers, and that certainly was needed for the keyboard, timer, serial port and mouse, and in the early days it was also necessary for the floppy disk controller. I'll be talking about in a second. We need a PC compatible keyboard, particularly all the scan codes and things like that the keyboard returns needs to be PC compatible. Now in the original PCs there was something called direct memory access and direct memory access controller, and this would kind of offload some of the data transfer from the CPU for dealing with things like floppy disk controllers. Now the Tandy 1000 PC Junior didn't include DMA, and in fact in the Breadboard PC version 1 I had a lot of trouble getting the DMA working reliably, and so I worked out a way how to avoid using DMA and used programmed I/O for accessing the floppy disk controller. So in fact in the version 2 of this Breadboard PC we're not going to be using DMA, and that will simplify things quite a bit. Now the reason why I think the IBM PC was so successful is because IBM published a huge amount of information about the PC in the technical reference guide, and you can see this one's some 628 pages long. And not only did it include all the technical details, it included the schematic diagrams and even the full listing of the BIOS. So you can see here full BIOS listing probably runs to about 70 or 80 pages, and also the logic diagrams. Now some of the other diagrams at the beginning are useful just for sort of getting a feel for the overall scope of the system. So this system block diagram I'll be going into in a minute. And then there are also a more detailed sort of system board diagram as well, which we're going to. And then when we get to towards the bottom, we then got all the logic diagrams, which again, I have got copies of these in the slides here, but I'm not going to be going into in-depth discussion of them because I kind of did that in the previous series. But you'll see here you've got the main system board with the processor and maths code processor and the various sort of timing and DMA, RAM board, additional RAM parity generation, expansion RAM, the timer and speaker output, the parallel port and keyboard interface, and the bus connectors. So all these are in there. I'll include the link for the technical reference guide in the description below if you want to have a look at that and see where you can go for this for the definitive information on it. Let's go through and have a look at these diagrams. So all I've done on the block diagram here is highlighted the bits that we're going to be looking at and all we've already done. So things like the processor, speaker, keyboard, read-only memory. We're not going to be bothering with a monochrome display adapter this time round. We're just going to jump straight to the CGA color graphics adapter. We've already done the communications port, and we will be looking at adding a fixed disk, a drive and adapter, but we're not going to be worrying with some of these other things, some things like light pens and printers and all that sort of stuff. Then this diagram is probably overcomplicated for purposes here, but the main thing really here is a lot of the complication here was caused by DMA, the DMA controller and the separate bus that it had, known as the X A and XD bus, and we largely avoid all of that by removing DMA, and as long as we include enough buffering on the data bus, then hopefully we won't really need complexity what we have here. The main differences we've got really are that in addition to the standard 14.3 megahertz clock that the original PC PCXT had, we're also going to have this faster 25 megahertz clock, which happens to also be the VGA dot clock frequency, and that should mean that we can actually run the processor fast enough such as we can talk to the floppy disk controller using programmed I/O rather than needing to use DMA. We're also going to be expanding the number of interrupts that we support. So the original PC only supported 8 interrupts. We need to have the 8 to 15 to be able to do things like the mouse and other adapters and things. And you'll see there's quite a few things which we don't need to worry about in this scope. And then as far as all of these diagrams, so you'll see that I've annotated all of these. So the main system board, this is the processor, but we're not using the maths coprocessor. Got all the buffering here. Then a lot of the control logic we don't need to worry about. A lot of this was related to DMA. We're just really going to do a bit to do with some of the wait states and things. So the ready wait in particular is used to extend some of the bus cycles for slower I/O devices. We need a bit of I/O decoding and memory decoding. We don't need to worry about the DMA controller at all, so we'll remove all of that. This is the ROM, although we don't need to worry about additional buffers and things for the ROM. We can just put that, we've already installed that and got that running. A lot of the complexity around running dynamic RAM and refreshing dynamic RAM and checking parity, we don't need to worry about either. And the RAM expansion, because we've got 2 chips containing up to 1 megabyte of RAM, we really don't need to worry about this complexity. Then we have the system timer. So this is the programmable timer, and we will be actually making use of this, although some of the circuits we'll be making use of comes from the XI8088. So in particular, the speaker output circuit will be borrowing from Sergey's design, and we'll also be adding a real-time clock as well. Now, the real-time clock only really got added from the PC-AT onwards, but we will be adding one of these in a couple of videos' time. So then this is probably the one which is of most interest within this video. So the original IBM PC and PCXT included this 8255 parallel port interface. Now this actually included 3 ports known as port A, port B and port C. Now port A was primarily used to access the keyboard and was used for the keyboard controller. Now because we're going to be using a PS2 keyboard, there's a dedicated controller for that, so we don't need to worry about that. Port C was primarily used for the configuration switches, which were how you would configure the memory, banks and various other options within the original PC and PC XT. But because we're using real-time clock with some CMOS back memory, the XI8088 BIOS allows us to do the configuration in CMOS memory, and so we don't need to worry about these either. So in fact, there's only a handful of the lines actually on port B which are used, and we'll be looking at the XI8088 information on this really rather than this, because you can see so much over here is actually in red and unnecessary. There are a few items and things here, but we'll be focusing more on the XI8088 information for that. And then finally, the bus signals. So those are the original IBM XT designs, and the majority of it is actually being used to base the original version 1 of the Breadboard PC. But there are some changes from that to simplify things for running on breadboards and to remove some of the problems that I had with DMA. So the XI8088 design from Sergey Kiselev, I'll include the GitHub reference in the description below. So this is the top level diagram, and really the bits in purple are the things that we're going to be working on. So you'll see this is the port B timer real-time clock, keyboard controller, some of the logic for the input-output chip select, but we won't be including the DMA related information. And I sometimes will refer to the KiCad schematic diagram here as I'm going through things where I'm trying to actually clarify things. So there are a few things that I called out here. There are some specifics to do with the original PC had special handling of slot 8 expansion slot. We're not going to worry about that. Adds complexity that we don't really need to worry about. So because we've removed DMA, we don't really need to worry about the X bus as it was known, so the XD and the XA address lines and things. Now, parallel port A conflicts in fact with the PS2 keyboard controller, but we don't need port A, and so that's not really an issue. We do need the parallel port interface port B on port 61, that is required and is in the XI8088 design. One thing we need to be aware of is that the PS2 keyboard controller, the A0 address line on it in fact connects to the A2 address line. So in fact the keyboard controller ports are 60 and 64. So that's just something when you're hooking these up, you need to be aware that you don't want to connect the keyboard controller A0 line to A0, you need to connect it to the A2 address line. I've consolidated the I/O ports and interrupt mappings, and you can see a lot of the information here. The GitHub site for Sergey, which includes the BIOS and the XI8088 schematics. So I've summarized the interrupts and the I/O ports that we're using and highlighted those ones in green where we are going to be using them and the ones in red where we don't have to worry about it. Originally in the IBM PC, the non-maskable interrupt was actually used for memory parity and also sometimes for some of the parity checking to I/O devices. So we're not going to use the parity in this design, and we in fact use it for the nanocomp monitor abort key. Allows us to jump into the monitor and inspect memory. So we're not going to be using the second serial ports and the parallel ports either. We will be using the real-time clock, mouse and hard disk interrupts here, and you'll see also the timer keyboard. I also see that interrupt 2 is in actual fact the cascade for interrupt controller 2. So in fact when we've got the 15 interrupts here with the 2 interrupt controllers, the original PC only had 1 interrupt controller, so it'd do 0 to 7, but in fact in order to cascade the 2 interrupt controllers, then interrupt 2 is in fact used for the interrupts being generated from the second controller. And down on the I/O ports, you'll see we're no longer using our original Motorola 6850 serial controller. We've replaced that with our serial port here in the previous video. And although we've still got the port assigned here for our LED display and keypad, and then all the other ones here, the main gaps really being we no longer got the DMA controller, DMA page register, and we'll be using the XT IDE hard disk controller and BIOS later, and that uses this port range is the default for that rather than the original IBM PC did use a slightly lower range for that. Let's take a look at the KiCad schematic to see what bits we're going to be adding here. Okay, so this is our top level diagram. I will publish these on GitHub. I just got a few changes to do to the CGA video controller before I publish it, just because there are some things that need to be changed. Most of the bits around here and here are pretty good now. There are not many changes to make here. So in the previous video, we added the serial controller here and the USB to PC serial port. And where we're going to be looking during this video is at the top right hand corner here. So we've got our CPU here and the clock controller and bus controller here. And we've already added the main address decoder, but what we're going to be adding during this video is the power on self-test port, our port B, which has 2 chips, one for reading and one for writing. We won't be doing the real-time clock for the moment. We're going to need to add an I/O port decoder, so this breaks out the lower 8 address lines into the appropriate signals for controlling these various chips around here. We're going to be adding the programmable interval timer, and there's also a chip here which is a programmable logic device which we will be using for providing the speaker output and some of the gate consolidation that's necessary for that, and it will also be used to generate some of the ready wait signals needed sometimes for wait states if we were dealing with slower I/O devices. Now for the moment I'm not going to plug in the system data bus buffer here. We're going to be doing that when I do the interrupt controllers. So for the moment I'm just going to be connecting these chips directly into the data bus. We will then change that in subsequent videos when we put in the interrupt controllers and our data buffer here. I did have some problems at the later stages of the project when I'd added a lot of extra items onto the original Breadboard PC, particularly I had the CGA and MDA video cards, which were actually using quite a lot of the data bus capacity. So I want to add more buffers in this version so that hopefully things will be a bit more reliable when the design has actually got a lot larger. So I've got two PLDs here. So we've got the I/O decoder PLD and the speaker timer and wait states PLD. I have already gone through and done the rules for that. Sometimes I forget to do this, so I'll just highlight the rules here. So basically these are all the chip select outputs for the various interrupt controllers, timers, the real-time clock, port B, power on self-test port, and also that data buffer that we've got there. And then similar to the earlier videos I've done, I'm now using this field syntax for the address. And this means that all we need to do is to refer to our IO 0XX range input. So this is an input that we've got from our main decoder that tells us when we've got an address in the lower IO port address range, 00XX range really there. And you can see here that these are the addresses for the various things which are in the diagram that I showed in the slide earlier. And this actually then just generates all of the necessary conditions with those address lines to satisfy those rules. And if we actually compile this, open in WinCUPL, we need to open an existing one like this first, turn off the project view, and then when we run it, compile, that's been successful. If we have a look at the documentation file, I'd always recommend you look at the documentation file. I neglected to do this a couple of videos ago, and I realized I'd made a mistake. You'll see that those rules with the field syntax have now expanded to all these A0 to A7 values. That makes the specification of these very much easier. And we'll just check that all the pin assignments are correct. Apart from the address field, everything else should have a pin assigned. This indicates if we've made a spelling mistake, for example, if we had something 0 here. Then if we go all the way down to the bottom, then we'll have a, no, in fact, you wouldn't expect us to have that on pin 1, in fact. Let's just check against the schematic. So in fact, pin 1 should be not connected. We're not using it for anything, whereas at the moment, we have actually got pin 1 is a legacy from the first version. So we're just going to remove that. Save it. This is why it's so useful to look at the documentation file. Just little things like this might cause problems at a later point in time. We turn this off and recompile it again. Now when we have a look, hopefully, yes, we've got rid of that now. So we've got our IO read, IO write, all the address lines in there. This other input here for our 00 port range, then these are all the outputs. That's okay. And then the other PLD we've got here, this has actually got a couple of complicated functions on here. And I'm actually using an ATF750C because we actually need this to have more than one clock signal to drive the flip-flops in here. And so what I've done, similar to earlier on in the video, I've actually got where the PLD rules are quite complicated. I've actually got the schematic for this is highlighted here. So there are several aspects of this. There's bits of the speaker output circuits. You'll see here that there's a speaker output from port B and also output 2 from the timer, and that produces a speaker out which goes off to the speaker circuit. There's also a toggle for the dynamic RAM refresh timer. So the original PC had a timer for refreshing the dynamic RAM, but that can still be used and is used by the Xi88 BIOS for doing timings. And so what this does is effectively toggles the dynamic RAM refresh timer on this pin, and this can be checked on port B. And then this circuit here is relatively complicated. If we have a look at the Xi8088 design, this is the bus arbitration and wait logic. So not only the wait logic, but also the DMA logic in here. And I covered this in quite a lot of detail in the previous series. But in fact, the only bit where you need to worry about is this bit for the wait states for the I/O ports. And so what I've done here, so basically just got whenever there's an I/O read or an I/O write going on, this actually will generate a wait state. So this extends the I/O access by an extra clock cycle, and this other flip-flop in here basically delays the reset to this flip-flop by 1 clock cycle. So what this effectively does is adds an extra delay 1 clock cycle to I/O reads and writes. So these rules have been encoded into the PLD. So we've got our inputs on here, and there's also the real-time clock has an active low interrupt which needs to be active high, so we actually invert the real-time clock signal out here. But the main thing's really got the speaker out going to the speaker circuit, to the loudspeaker. We've got our ready wait output which goes down to our clock controller, clock generator, and will pause the CPU if it needs extra time. The refresh det signal here is used by the BIOS actually to check up on the refresh timings, and it's used that for certain delays if you want to make a more accurate delay linked to that timer. And because this is a 750C, it means that we've actually got more options to us. We can have a separate clock for each flip-flop, and you'll see here that the ref det, for example, is using the out 1 from the timer. It has a dedicated reset, and in fact the diagram here shows that the input, the D input, is actually coming from the inverted output, and so the D input is actually coming from the inverted output. Then I've generated this combination between the I/O read and I/O write. This is effectively the NAND of the I/O read and I/O write. This is this gate here. This input generates a clock. Now there is a limitation of the 750C, is that we can't include sort of logic terms for the input clock. We kind of need to consolidate these together as an output pin, even though we're not directly using that output pin, then feed into the clock here. So this is the main ready wait output. So the ready wait output is just connected directly to the pin. But this is the second flip-flop that's actually clocked off the main CPU clock. The input to it is actually coming from the output of the previous one above. We don't have any preset values, but the reset for this one is actually coming from the reset signal itself. Whereas the reset input to this one is in fact the inverted ready wait one from here. And if we go back to the diagram here, you'll see that in fact the output here, the output of the delayed by 1 is going into the reset here, and the output of the ready wait one is going into the D here. So by putting these diagrams in here, it just makes the logic rules a bit easier to get right. So hopefully I've got those right. And if we just compile this one, compilation successful, we'll just open that one, documentation file for that one. If we look at all the sections here, we can see that in fact our ready wait in fact is using a pin node, so it's not directly assigned to a pin. It's kind of an internal thing. And if we look at the documentation, so what we can see actually in the 750C documentation is we're actually making use of one of these second flip-flops here, in fact, for our delayed ready wait by 1. So we're making use of one of these, which requires us to define this pin node, which I covered in the PLD series. So I include a link to the PLD series, which I covered some of the more complicated aspects of this, including how to use all of these pin node extensions and things, these more complicated 750C PLDs. One thing to note is you do need the more advanced programmer to program the 750C. You're not going to be able to use a basic EPROM programmer for programming these chips, unfortunately. So I've already laid out the boards for these. So when we did the CPU, we actually laid out these sort of 4 breadboards already. So all I need to do now is we'll go off and we'll lay the chips out here. We'll start to wire all these up. And when we come back, we're going to have a look at a bit of the test software. So I'm going to do test to output to the power on self-test port, and we will also do a simple test to make sure we can get a diagnostic tone out of the timer through to the speaker. Okay, so I've laid out the board. This is similar to what we had before. Slight change that I've moved where the speaker is going over that side. This is where the real-time clock will go in subsequent videos and the backup battery for the CMOS. So just wanted to make sure those are all going to fit in, so we can take those out now. All the chips got labels on. I've labelled up all the port B and write and read so that they've all got the right pins on there. I'm just going to put all those in and then we're going to wire them all up. Now the data bus is going to be coming from the main bus rails. Now it doesn't quite fit this timer chip here. So what I'm going to do is to bring it in over here initially, because we're going to be putting the buffers in interrupt controllers over this side of the board here. So the buffer is going to have a cable going from there to there and from there to there. So we'll put it in here for the moment. And I've also got the A0 to A7 lines coming in from down there. So that's where those main ones are going to go in there. So we don't have to worry about those. Now we just need to put in all of the power lines, decoupling capacitors, and when we come back we should be ready to start testing the speaker, timer and the power and self-test port. Okay, so first going to do the power rails and those pins tied to 5 volts and to ground. So we've got various gate signals and output enables that need to be tied to 5 volts and ground. So putting in the power, that's an enable. Various unused inputs onto there are tied to ground. An output enable there. And this is the gate 2, which actually comes from port B, enables to turn on and off the oscillator for the speaker. A couple of extra gate ones there as well. So now we're going to do the chip selects for the power and self-test port and port B read and write. That's the power and self-test. Now I had actually got the labels around the wrong way on the chip label for the read and write there. So now we're going to do the IO0XX range there, and also the IO read and IO write lines are going to feed up from the main address decoder down there up to the IO decoder, and then we'll also be wiring that up for the higher up chips in a minute. Now we're going to do the programmer interval timer chip select and feed the IO read and IO write further up there to the timer. Now we need to wire in the IO read and IO write going up into the ready wait speaker PLD, and also we need to feed the A0 and A1 into the timer chip there. Again, the label on the PLD there had A0 to A7 in the wrong way around, so I needed to change that later. Now we need to wire the clock inputs to the timer to the hit clock, which is about 1.18, 1.19 megahertz. Then the output there is used for the refresh of the RAM originally, and we also need to plug in the reset. And we'll also wire in the hit clock as well. That's the out 1, the reset, and that is the clock going into there and the reset going up to the PLD up there. So now we need to wire in the speaker and the out 2. So out 2 is the oscillator for the speaker and the speaker enable, and then wiring in D2, D3 to the right port B there. Now I need to wire up the out 2 and the enable IO check turbo, which selects between 14 and 25 megahertz, and the gate 2 signals there. That's out 2. That's the ref det, which is like the refresh. And then we've got the turbo going in the bottom there, speaker and gate 2. Then I just need to wire in the D0 and D1 for the port B there, and also the main system clock, clock 88, which is like 4.77 megahertz normally. And then we've moved the speaker circuit over to the right hand side here. That has a transistor, a couple of resistors and a capacitor. Just going to wire that in. Now IRQ8 comes from the RTC and needs to be inverted, but it's not in use at the moment. And also we're not going to be using the ready wait at this point in time, but we could introduce wait states if we want to at a later point. Now we just need to wire in the data bus really between the various chips here. Just plug in the DuPont cables between those. Okay, so finished hooking up everything now. So the speaker's plugged in here. What I'm just going to do is unplug the speaker output from the logic chip there, and we're just going to attach a signal generator on here. So here's one of the logic analyzers I've got. I'm just going to hook up the power on self-test port to that, and there's also an oscillator output that we're just going to feed into the output stage here for the speaker just to make sure that's working okay. And if you also have a look at the test program that I'm using for this. This program's based on the test program that we had for the keypad and LED display. And all this is going to do is to write some values to the power on self-test port, and also is going to configure the timer to do the 400 Hz speaker beep, which is one of the error codes when there's a CPU error under the BIOS. So all this is going to do is to write post-test, first of all, to the display. Then once we press a key, it will then loop through writing the FF down to 01 to port 80, which is a power on self-test port. And after that, it will be beep test, wait for a key, and then what this code here is going to do is to configure the programmable interval timer for a specific frequency, which should be about 400 Hz. So it should be the same as the beep that I'm going to do with the signal generator. And then this should then actually beep, and then when we press the key, it should then stop. So we just need to assemble that. Okay, so that's assembled. Just check the listing file. Yep, so that looks like it should be okay. So I'm just going to plug in the logic analyzer, and we're just going to test the oscillator going into the beeps first. Okay, so I've plugged in the signal generator into the input from this yellow wire here that goes into the speaker output from the logic there. We've also got the data bus for the power on self-test port, and there's also the chip select for the power on self-test, so we're going to trigger things on that. So first of all, I'm just going to turn on the computer, and because we've got the signal generator going directly into the speaker, when I turn it on, we should just hear a continuous tone. So I'm just going to put the microphone closer to the speaker here, and we'll turn it on. You should be able to hear a continuous tone. Sometimes the noise cancelling gets rid of the tone, but as a continuous 400 Hz tones, that means the speaker output's working. That's good. Just disconnect the signal generator and plug this into speaker output. Okay, so after I did the testing of the speaker there with the signal generator, then I didn't get much further, though I had some problems. And what I eventually found out is that I had inconsistencies in the order of the address lines, so A0 to A7 on this decoder here, and somehow I'd managed to have one set of documentation. So the KiCad and the chip labels had it one way, and the PLD configuration had it the other. So I've now changed those all to be consistent, put a new label on it, and now it's all working. So I'm just going to move the camera over to the keypad so we can actually see the software being loaded, and then we'll also have a look at the logic analyzer to see what we're going to be looking at there. Here's the logic analyzer. We've got the first 8 lines of the power on self-test port, so we'll get those codes decoded here. That should go from FF down to 01. There's a number of other signals here, including the post power on self-test chip selects. That's what we're triggering things on. And there's also other things here. The out2 is in fact the output of the timer into the speaker to generate the tone. Just to show you, so this was the way how the PLD was configured. However, when I did the chip labels, I had 7 here down to 0, and also the KiCad was similarly 7 down to 0. So when I was doing this, I obviously got my wires crossed somewhere along the way, but that's all now consistent and all fixed. So what we're going to do now is power on the computer, download the program. So this is our post beep test V1. There's one other minor issue I needed to fix as well. For some reason, I originally had this loaded in the 7000 segment, and I had 1 or 2 problems with some bytes being overwritten. I suspect some of the monitor is overwriting some bytes somewhere, so I changed it to the 6000 sort of range, and everything seems to work okay. So here we have the LED display and keypad for the monitor, so I'm just going to power this on. So we've got Nanocomp 8088 version 7. So all I'm going to do first of all, I need to set the extra segment to now 600, code segment to 6000, so this is where we're going to run it from. Now I'm going to go into load, just now going to send the srecord file down. That's now finished, and if we just check 0000 just to see the FA is disable interrupt, so that looks like that's loaded okay. So I'm just now going to get this lined up to start, and we just now need to get the logic analyzer ready to run, and I'll just press 0. So we've got power on self-test. When I press this button, it's now going to start writing the power on self-test codes to the logic analyzer. I'm going to press the key a couple of times and we should hear the beeps. You may not hear the beep that clearly because the noise cancelling on the microphone quite often cancels it out. I'll press this for the beep. You might be able to hear this. And then it stops. And then we get the registers. We can see all the register values there. Okay, that seems to be working. So if we just go back to the logic analyzer here, see what you'll see at the very beginning here. This is triggered on the power on self-test. And what you can see here, the host port has got FF, FE, FD. If you look down the right hand side here, you can see this is going all the way down to 01. That looks like what we'd expect. And then if we zoom out a little, what we can see here, this is the programmable interval timer, where basically we're setting up the 400 Hz tone on there. And then you can actually see that this is the out to where the output of the programmable interval timer is actually giving us, if you look up the right hand side here, the frequency there, that frequency is 400 Hz. That all appears to be working. So now just have a look at where we've got to. So we've now completed the power on self-test port and port B as well. We'll do a bit of testing that in the next video, particularly the turbo mode and things like that, which is a higher frequency version. And then we've also tested the timer and the speaker. So in the next video, we'll be looking at the interrupt controllers and the real-time clock. And we'll be starting to get the BIOS configured and see what sort of information we can get for the BIOS. So if you don't want to miss out on future videos, then please hit subscribe, and if you can hit like as well if you found the video interesting, it just helps to make the videos available to more people. Thanks for watching.